Very good morning to one and all. So we are discussing
Good
how
morning,
to
sir.
morning. So we are discussing how to find out the equivalent resistance of a network. Okay. So I think this problem is done. You may done. Okay. So that is here in this case, you have to find out the resistance across A and B. You have to find out the resistance across A and B. So in such situation, we have to see the where that resistors are in series and where the resistors are in parallel, in such that we can observe. Okay, so if you see here, 2 and 6 are in series, and the combination is 8. The resultant value is 8. Okay, and for here we have 8 and 8. These two resistors are in parallel. When two resistors are in equal values, or two equal resistors are connected in series, the resultant resistance value is half of the single resistance value. So here 8 are equal, so the resultant resistance value is 4. Okay, so these two are replaced with a single resistance value of 4, and then here we have another 4 ohms resistor. These two resistors are in series, then 4 plus 4 8. With this series combination we get the 8 ohms. Here we get the 8 ohms. Now these two are in parallel. 8 ohms are again in parallel, and the resultant resistance value is 4, because two equal resistances are connected in parallel. So the resultant value is 4. And coming to here, 6 into 6 and 3 are connected in parallel. So this is R1 R2 by R1 plus R2. 6 into 3 by 6 plus 3. So 18 by 9. So that is to 2. 2 plus 4. It gives 6 ohms. Finally, we get the total resistance is the 6 ohms. Okay. So like this we can do the. Okay. This is the another problem. So we have to find out the resistance across A and B. You have to find out the resistance between A and B. So the simple solution I was explained. First, note down the two nodes A and B as it is. Okay, start from A, and how these are connected you can represent. From A, you have to start, and how to reach the B. So one way is 4. See here, there is no connection between these two lines. These two lines, there is no connection. This is overlapping. There is no connection. Please remember such things. Okay. If there is no overlapping, then it is joint. There is a joint. Here there is no joint, because one wire is passing through over the another wire. Okay. So this is the 4 ohms resistance. Okay. So after that, consider this the point of D. Okay, this is the point of D, and from D to 2 ohms resistor is connected to B. From D to 2 ohms resistor is connected to, this is A, and this is the B. Okay. So this is the 2 ohms, and this is the 4 ohms. Okay. Next, another combination is from A to we have another branch, that is 6 ohms. From A to we have another combination 6 ohms. So 6 ohms is connected to 8 ohms, and it is connected to B. Okay. So here 6 ohms is connected to, as well as connected to D, as well as connected to 8. So it is connected to D as well as connected to 8 and connected to B. Okay. So here this is the 6 ohms and this is the 8 ohms. So you can see this point and this point both are same. So this is D point. Okay. Both are same points. Okay. So this entire thing is the D. Okay. From 6 to 8, while going it is connected to D. So that's why I was connected to this line. Okay. Now observe 4 and 6 are in parallel and 8 and 2 are in parallel. 4 and 6 are in parallel and 8 and 2 are in parallel. The obtained two resistances or equivalent resistance are in series. 6 into 4 divided by 6 plus 4. So 6 into 4 it is 24. That is R1 by R1 R2 by R1 plus R2. 24 by 10. That is equals to 2.4 ohms. Okay. So the equivalent of this combination is equals to 2.4 ohms. Okay. And for coming to here, it is 8 into 2 divided by 8 plus 2. R1 R2 by R1 plus R2 combination. Parallel combination. So then it is 8 2s are 16 divided by 10. 8 plus 2 is 10. So it becomes as 1.6. 1.6. Okay. So 1.6.
4 ohm.
Yeah, it is 1.6 plus 2.4. It is equals to
4 ohms.
4 ohms. Okay, because after this, these two are in connected in series. That's why its value is 4 ohms. Okay, the net value of A and B is the 4. Okay, clear?
Yes.
So similarly, here we have another one. Same previous one only. Like so here we have previous network, previous problem we are seeing. So that is up to here it is the same. Up to this part it is the same. So up to this it is having a and B, and we are derived, that is equivalent resistance of this particular A and B is 4 ohms. 4 ohms. Okay. So that is here it is 12 volts, and here we have another resistance 4 ohms, and up to this point it is 4 ohms. Now this 4 ohms resistance and we are derived 4 ohms resistance. Both are in parallel. The net resistance is 2 ohms. The net resistance is 2 ohms. Then find out the I. I is equals to V by R. I is equals to V by R. Okay. So that is V is equals to 12 volts divided by 2 ohms. That is 6 amperes of current. I is equals to 6 amperes. Like this we can solve the equations. Okay, like we can solve the we can obtain the current. Okay, you understand now? So up to this right side of this part is the same as previously we are solved. Okay, so we obtained, that is 4 ohms resistance. Okay, so another 4 ohms resistance is connected in parallel with these two terminals. So that's why 4 ohms combination produces the 2 ohms. So the total resistance is the 2 ohms. Okay, then I is equals to V by R. 12 by 2 gives 6 amperes of current. To find the current I. Okay. So like this we can find out the current in a given circuit. So here we have the first circuit here A. In the circuit we have to find out the resistance across A and B. To find out the resistance across A and B. So for such situation we have to come from the right side. So here 4 and 2 are in series. Equivalent is 6. And after obtaining 6, here we have 6 ohms. So 6 ohms are in parallel. The resultant is 3. 3 plus, again this is in series. So 3 plus 2 it is 5. So 5 is in parallel with 2. 5 is in parallel with 1. 5 is in parallel with 1. Then gives the 5 by 6. R1 R2 by R1 plus R2. 5 into 1 into 5. 5 plus 1 is 6. 5 by 6. Like this we can obtain the resistance between any two terminals. Suppose I want to find out the resistance across E and F. Then these two resistors are connected in series, 3 ohms, and after that it is in parallel with the 6 ohms. Okay, So we will find out the parallel resistance. After that, the obtained value is in series with 4 ohms, and that obtained resistance is in parallel with 2 ohms. Like that we can find out. Suppose we have to find out resistance between C and D. In such situation, 2 and 1 is series. Here it is 4 and 2 are in series. The obtained 2 resistances are in parallel with 6. So 3 are in parallel. So find out the parallel resistance across three branches. Okay, like that we can find out the resistance between any terminals. Okay, so with this we are discussed about the how to find out the equivalent resistance of a circuits. Okay, the next concept regarding the Kirchoffs laws. So what are these Kirchoffs laws? So what purpose we can use? The Kirchoffs laws are nothing but Kirchoffs voltage law and Kirchoffs current law. There are two laws are there. The laws are more comprehensive than Ohm's law. So these are more useful while solving the some networks which are not which are not possible to solve by using the Ohm's law. Okay, and these are two types and generally useful for determining the equivalent resistance of a complicated network of conductors. So a network is having just we are saying a small network. We have a large networks and complicated networks will be there. In such situation, it is not possible to determine the different parameters using Ohm's law. In such situation, we have to go to the Kirchoff's laws. And these are also used to find the current flowing different conductors. Okay. So the two laws are Kirchoff's point law or current law. So you can simply call it as KCL. Kirchoff's current law. And second one is Kirchoff's mesh law or Kirchoff's voltage law, KVL, KCL and KVL. Remember these two, important. Definitely they will ask one question. What are the Kirchoff's laws? Okay. So KCL and KVL, Kirchoff's current law and Kirchoff's voltage law. So we will explain what is the Kirchoff's current law and what is the Kirchoff's voltage law. So Kirchoff's point law or current law. So it states, so in any electrical network, the algebraic sum of the currents meeting at a point or junction is 0. Suppose we have a junction. Okay, so at that junction, there are some currents are coming and some currents are going. Just like in our traffic, we have junction. So for the junction, some traffic is going outside, some traffic is coming inside. So like that, in a given network, we have number of junctions. So at a given junction, so there are number of currents will coming towards the junction and number of currents will be flows out of the junction. Okay, so in such situation, for that particular junction, the number of currents coming is equals to the number of currents going out. Okay, that we can write it as algebraic sum of the currents meeting at a point or junction is 0. Okay, some points are some currents are coming inside, you consider as positive, and currents which are moving that junction is considered as the negative. Then the sum of the currents which are that is called as incoming currents is equals to outgoing currents. Okay, so the sum of the incoming currents and the sum of the outgoing currents both are equals to 0. So the total current leaving a junction is equal to the total current entering the junction. So it is obviously true because there is no accumulation of the charge at the junction of the network. Because at that junction there is no charge accumulation is not possible. So that's why how much current is coming, that entire current is going outside. It is not stored at the junction. So that's why the sum of the currents entering a junction is equal to the sum of the currents leaving the junction. Simply you can say the sum of the currents entering a junction is equals to sum of the currents leaving the junction. So you have considered this figure. You see the A figure. So in this A figure we have I1 is coming towards A. This is the junction. A is the junction, and I2 is leaving from the junction A. Okay, I3 is also leaving. I4 is coming towards the A. So this is incoming current, and this is I5 is leaving the junction. So this is outgoing current. So incoming currents I1 and I4, and outgoing currents are I2, I3 and I5. So the Kirchoffs current law is saying that the sum of the incoming currents is equals to, very easy. So the sum of the incoming currents is equals to sum of the outgoing currents. So with these directions we can find out which currents are coming towards A and which currents are going out of the this junction A. Okay. From that we can find out the I1 plus I4. These two are incoming currents, and from here I2 and I3, I4 are outgoing currents. Sum of these currents I2 plus I3 plus I5, and both are equal. So the sum of the I1 plus I4, sum of the I1 plus I4 incoming currents is equals to sum of the outgoing currents I2 plus I3 plus I5. So this is nothing but the Kirchoff's current law. Okay. So for this diagram, so I1 is coming, and I1, sorry, I is coming, okay, and I1 is leaving, I2 is leaving, I3 is leaving, I4 is leaving. So at this point of junction A, so the total current, incoming currents is equals to sum of the outgoing currents. Sum of the incoming currents is equals to sum of the outgoing currents. So sum of the incoming currents is only single current is coming, I, and that is equals to I1 plus I2 plus I3, I4. So these are outgoing currents. I is equals to I1 plus I2 plus I3 plus I4. Like this, we can get the Kirchoff's current law formulas. Okay. So that is explained here only. So incoming currents is equals to outgoing currents. And second one is Kirchoff's mesh law or voltage law. So that is called as KVL. KVL, Kirchoff's voltage law. So in this, suppose we have considered a circuit. So in that circuit, we can see the voltage sources and resistors. So for the voltage sources, we have a number of voltage sources, that is the EMFs, and the voltage drops due to the these resistors we have. So summation of all these, the algebraic sum of the all the voltage drops and voltage potentials present in a loop is equals to 0. Okay. So suppose I will show you. So in other words, so IR is nothing but I into R, that is the voltage. V is equals to I into R. Okay. So this is this is for the resistors, okay, that is called as voltage drop. So for the corresponding resistance we have the voltage drop, and EMF is nothing but the applied voltages. Okay. So the applied voltages, okay, the sum of the voltage drops of the resistors plus sum of the EMFs present in a network. Okay, and that is equals to 0. The sum of the voltage drops is plus the sum of the EMFs is equals to 0. That is algebraic sum of the EMFs and the voltage drops is equals to 0. Should be noted that algebraic sum is the sum which takes into account the polarities of the voltage drops. See here. So from figure A, so Kirchoff's analysis for the above mesh A is given in B and C. So this is the a mesh. We can say it is network. It is a network. So this is the voltage source V0, and we have resistors R1, R2, R3, R4, R6, R7. Okay, and here the junction. This is the junction point. So R1, R3, and R2 are joined here. So this becomes as one node. Similarly, here also we have another node. So this junction point is considered as, the junction point is called as node. The junction point is called as node. Okay. So here in this particular case, it is having, this is the two nodes, and here also we have another nodes. So this is the node, this is the node. Okay, and one particular line is considered as branch. So from this junction point we have a branch. So here this is a branch. Okay, so coming to figure B, so this is the node what is presented in A. So this is the node. For this node we have incoming currents I1, I2 and I3. Okay, so for this node there is direction of the currents I1, I2 and I3. So by using the Kirchoffs current law, the sum of the incoming currents is I1 plus I2 plus I3, I1 plus I2 plus I3. Okay, and some of the currents out. So there are no output currents, but we're considering these are negative of the input currents. So that's why these are minus I1, minus I2, minus I3. So there are no outgoing currents. So outgoing currents is opposite to the input incoming currents. That's why these I1, I2 are represented in terms of the negative also. So that is minus I1, minus I2, minus I3, and that is equals to 0 amperes. And coming to this one, this is a mesh. So remember that Kirchoff's current law, KCL law, is applied for the nodes, whereas Kirchoff's voltage law is applied for the mesh. So mesh is nothing but a closed loop. So from this point it is closing. So it is closed loop. Okay. So it is closed loop. Okay. Uh, so here we have different voltages. So across this resistor we have a plus V5. So V5 volts. So this is a V8, and the voltage drop across this resistor is V6, and this resistor we have V7. Suppose we are started. Suppose we have to how to can get these voltages. So from here we can draw one line. So in this direction, go in this direction from this point. So what is happening? So from plus to minus. So this is minus V5. Okay. So there is a drop. See here, when we are going from plus to minus, it means there is a voltage drop, and from after that this is the plus to minus, again it is voltage drop, minus V8. So this is minus V8. Okay, and this is the minus V5. Okay, and after reaching here this is also minus V7, and here it is minus, this is the minus V6. So summation of all these is equals to 0. If you go in clockwise direction, we will get minus V5, minus V8, minus V7, and minus V. This is the minus V6, not plus. This is minus V6, minus V6. Okay, so that is equals to 0. Suppose we have to move in clockwise direction. Sorry, anti-clockwise direction. Suppose we have to move in anti-clockwise direction, then this becomes as potential rise. Previously it is potential drop. Now it is potential rise. So that is plus V5, plus V5, plus V6, and plus V7, plus V8. So like this we can write the voltage drops. Okay. So here we can remember that. So when we are moving in any direction, we can move any direction. Okay, but entire network we should follow one particular direction only, either it is clockwise direction or whether it is anti-clockwise direction. Suppose if you are moving in the clockwise direction, you will identify the voltage drops here. So this is plus to minus, this is voltage drop, then it becomes as minus V5. Here plus and minus, this is the V8, voltage drop across this resistor is V8. So then the voltage drop is minus V8. Like this we have. Suppose we have to move in anti-clockwise direction, this becomes as plus V5 and this becomes as plus V6 and this is plus V7. Summation of all those voltages is equals to 0. So first one is you have to start from any particular junction and go around the mesh till we come back to the starting point. So that is the important. So in previous loop, we are started from here in the clockwise direction. Again, we have to reach that particular point. Until that point, we have to note down the voltage values. Then we must be at the same potential with the which we started. So sign of a battery. So a rise in voltage should be given as positive sign and a fall in voltage is given as negative sign. Okay. So rise in voltage is considered as a positive and fall in voltage is considered as the negative. Okay. See here. So with this figure plus minus and positive and negative and positive. Okay. So with this is the rise in voltage. When we move in this direction, so the voltage is rise in voltage, that is represented as plus E for the batteries. And similarly this is negative and positive. Okay, from positive to negative. Okay, so this becomes as fall in voltage. Okay, then it becomes as minus E. Okay, so this is for the voltage sources. And for coming to the resistors, so this is positive and negative. So current is moving in this direction, we are also moving in the same direction. Current is flowing in this direction, we are also considering in the same direction. Then there is a voltage drop, so that is becomes as minus I into R, okay. So that is minus V is equals to minus I into R. And suppose the current is moving in opposite direction, so we are moving in a forward direction, then it is rise in potential. Okay, so that's why it is going to be considered as I into R. So like this we can represent the voltage fall while voltage rise in battery and voltage drop and voltage rise in resistors. So important point here we can remember is the sign of the battery is independent of the direction of the current. Okay. So direction of the current, so the sign of the battery is independent of the current which is flowing through the circuit. So this is the sign of IR drops, that is voltage drop across the resistor. So same as explained previous only. The voltage fall should be taken as negative. Same voltage fall is taken as negative and voltage rise is taken as positive. The sign of the voltage drop across resistor depends on the direction of the current through that resistor, but it is independent of the polarity of any other source of EMF in the circuit under consideration. Yeah. So here, see, so in this network, you will see from here I1 is current is flowing through R1, I2 is moving to R2, I3 is moving in this direction to R3, and this is I4. So for this we have to first we have to note down so when the current is moving through the resistor, current is decreasing. So before the resistor and after the resistor is different current is there, because this resistor will offer the flow of the currents. That's why before the current is very high, after this resistance the current is decreases. Due to that, this is the positive and this is the negative. Due to that, there is a voltage drop. This will be considered as voltage drop because the current before the resistor is before the current before the resistor is higher, okay,
Right.
than the current of the resistor R1. So that's why this it will be considered as a voltage drop. That is I1 into R1. I1 into R1. So this is the negative. Similarly, here in this case also, this is I2 into R2. So this is the plus and this is the minus, and this is also considered as minus I2 into R2. I2 into R2. Similarly here, this is the plus and minus, and this is the R3 into I3, and here it is plus and minus I4 into R4. So now we can write the voltage drop equations. Voltage drop equations. Here this is the, suppose we are moving, we are considering this the current direction. Okay, so this is the same entire the circuit. Okay, so if we are moving from this A to, again we have reached the A. So starting from A, so what is the voltage drop here? I1 into R1, that is negative. So minus I1 into R1. Next, this is minus, this is the fall in voltage. That's why it is I2 R2.
Minus R.
Minus, yes, minus I2 R2. Minus I2 R2. And here it is plus I3 R3. So where we are moving in this direction. Okay. So here it is the rise in potential. Rise in potential because minus to plus. Okay. That's why this is plus I3 R3 plus I3 R3. Okay. So after reaching here, this is minus I4 R4. Minus I4 R4. Okay. So this is the summation of the voltage drops. Okay. So next we have voltage sources here. So we are moving in this direction. Okay. So then this is the plus. So plus E1. So this is the voltage rise plus E1. Next, this is the, after moving in this direction, this is becomes as the minus E2. Minus E2. Okay. Minus E2. This is the minus E2. This is the plus and minus. Okay. This is the minus and this is the plus. Okay. So this is the plus E1. This is the minus E2. So summation of all these voltage drops of the resistors and the voltage EMFs is equals to 0. So that is E1, okay, E1 minus E2, and sum of all these voltage drops is equals to 0. That is the KVL, Kirchoffs voltage law. So the sum of the EMFs and the voltage drops is equals to 0. So then E1 minus E2 is equals to all these negative. Okay, so negative potentials are sent to right side. We can get I1 R1 plus I2 R2 minus I3 R3 plus I4 R4. Okay, so I think you catch this point. You understand this concept, I hope. This is also very important. So application of KVL and KCL laws to a network. So that is given here. So I1 R2. I1 R2 is fall in potential, I2 R2 is fall in potential, whereas I3 R3 is rise in potential. I3 R3 is rise in potential, and I4 R4 is fall in potential, whereas E2 is negative, fall in potential. E1 is positive, rise in potential. Okay, so like this we have. So by using Kirchoffs voltage law, so minus I1, this is there is some notation change is there. So this is I1 R1, I2 R2. So this is the I1 R1, not R2. This is I1 R1. So minus I1 R1, minus I2 R2, minus I3 R3 negative, and this is the minus, and also here this is the positive. See here, this is the R1, I1 R1, and here is the correction, that is I3 R3 is the positive, not negative. Positive. Okay, and I4 R4 is the negative, and E2 is the negative, and E1 is the positive. Okay, so by taking on the right side of the equation that we get E1 minus E2 is equals to this equation, I1 R1 plus I2 R2 minus I3 R3 plus I4 R4. Like this we can get the voltage drops of the resistors and voltage sources, potential drop, EMFs. Okay. Please note these changes. Okay, here it is the plus, and here is the I1 R1. So once a particular direction has been assumed, the same should be used throughout the solution of the equation. Okay, so for you have to follow one particular direction. So whether it is clockwise direction or anti-clockwise direction, so you should follow that direction entire solution. Should be noted that the Kirchoffs laws are useful in the application of DC and AC voltage currents. So it will be also applicable for AC